In this video, we're going to talk about the chain rule for functions of several variables. So remember from before, the total differential of a function of several variables is just the partial with each of the partial of the function with respect to each of the variables that make up the function times the differential of each of those variables and then add together. So here's partial with respect to x1 times differential with respect to x1 and so on for x2 and all the way down to xn. That's our total differential definition. So let's suppose that each of our variables here is a function of another variable. Say t1 out to tm, and then this is a typo, this should be an m. Well, if I think about taking each of these t1, whatever the functions are, and plugging it back into the original, then our function f will also be a function of the t1 out to the tm's. So we should be able to take the partial of f with respect to the t's. All right. So this is not what we're really doing, okay? But let's divide both sides by the dti, or partial ti, whichever you want to call it. Now remember, that really doesn't make any sense. dti is a notation. It is not a quantity, okay? However, the reason why we like Leibniz notation is because it is suggestive. It suggests what the formula should be. All right, so if I do that and divide through by the partial everywhere, the partial of f with respect to ti should look like this. Notice that we take the partial of f with respect to x1 and then the partial of x1 with respect to ti. Do the same thing for x2. Do the same thing all the way through for xn. Now, like I mentioned here, this 100% not a proof. I'm dividing by a notation that does not make mathematical sense. However, again, the reason why we like Leibniz notation, it's a very subjective notation. It suggests what the formula should be, and in this case, it works. Okay? So this is the correct form of what we refer to as the chain rule for functions of several variables. Notice that each individual term in our sum here looks like the regular old chain rule back for a function of a single variable. All right, let's see if we can try this out. We have a function w in terms of x, y, and z. A function, x and y are functions of r and theta. We want to find the partial of w with respect to r and partial of w with respect to theta at those particular values for r and theta. Let's use the chain rule to do it. Now, again, we could brute force it. We could take r cosine theta, plug it in for x, take r sine theta, plug it in for y, take r squared, plug it in for z, and brute force it and just do the derivative. But we want to be a little bit more elegant and use the chain rule here. All right, so partial with respect to r, basically it looks like we're just putting in x and y and z here as a form of 1 so that they would cancel out, so we really haven't changed anything. Again, not really what we're doing, but it owns to the suggestive nature of the Leibniz notation. It's why we like Leibniz notation, not because it's easy to write down by any stretch, but the fact that it actually suggests what's supposed to be going on. All right, looking at the function, partial with respect to x. You get a y and a z and a 0. So you get y plus z. Partial of x with respect to r, it's just a cosine theta. Partial with respect to y, you get an x and a 0 and a z. Partial of y with respect to r is a sine theta. For partial with respect to z, you get an x, a 0, an x, and a y, so you get x plus y. Partial with respect to r for z is a 2r. Do the exact same thing, but for theta. Notice that your y plus z, your x plus z, and your x plus y here technically don't change, right? Because this is partial with respect to x, partial with respect to y, partial with respect to z. That's where the y plus z, x plus y came from. The thing that's going to change are the partials with respect to theta. Going up to x, partial with respect to x is negative r sine theta. Partial with respect to y with respect to theta is r cosine theta. And for z, the partial with respect to theta is 0. Now it's just a matter of plugging in 2 and pi over 3 for r and theta. Notice I have to kind of do it in 2 steps. I got to plug 2 and pi over 6 for x, y, and z. So you get square root of 3, 1, and 4 for those values. And now plug everything in to your formulas here and get this answer of 6 plus 7 root 3. Do the exact same thing for the partial with respect to theta. Plug in your numbers and you'll get negative 2 plus 4 root 3. Again, this at the end here is just plugging in your numbers, right? And again, the intermediate step is to plug in for r and theta and get your x, y's, and z's so you can plug those into your formulas in your chain rule. Let's do one where you're not given explicit functions. So let's say we have a table of values here, and they tell you how x is defined in terms of t and how y is defined in terms of t, and it wants you to find the derivative of f with respect to t at 2. First thing that we notice is that when t is 2, x is 3, and y is 6. Just plugging those into the functions for x and y. All right, we can take the derivative of x with respect to t. We need to use a little chain rule action there. Take the derivative of y with respect to t. Again, use a little chain rule action there. Now we'll use the chain rule for functions of several variables. I don't have an explicit formula for f, so I don't know what to write for partial with respect to x. Okay, so I just have to write it in the formula. And then times the partial with respect to t, partial with respect to y, times derivative with respect to t. Notice that we said that x had to be 3 and 6, right? So notice I'm looking at the partial with respect to x evaluated at 3, 6, and for x and for y, not for 1, 2. So this first row is irrelevant. It's the second row we need to use. So partial with respect to x is 7, partial with respect to y is 8 for those two pieces. And if you go through and simplify, you'll get 244 over 3. Oops. All right, we can also use the chain rule idea for implicit differentiation. So this one asks us to find dy dx if that we have that relation. All right, so if I call z equal to f of x, y, let's suppose that f of x, y is equal to 0. So we just plug in 0 for z. Certainly, x is a function of x. We can treat y as some unknown function of x. By the chain rule, we've got x is a function of x, y is a function of x. We don't know what it is. But that we do know that the derivative of x with respect to itself is 1. So that term goes away. Also, the derivative of f with respect to x has to be 0 because the function is equal to 0. So we get this equation now to solve. Pardon me. So we have partial with respect to x plus partial with respect to y times dy dx. And now we can solve for dy dx. This gives us a nice way to do implicit differentiation without having to go through all the equation solving that we did back in Calc 1. So let's go rewrite their original equation here so that we have f of x, y equals 0. So just subtract your e to the x squared y over to the other side. Now we do partial with respect to x on top, divided by partial with respect to y, and put a negative out in front. So we have to use a product rule on top for derivative with respect to x. That's what this term is. And I forgot my 2x here. There should be a 2x in here too. The derivative of the x squared would be a plus 2x. There's a term missing here. And then for the other piece here, derivative with respect to x would be 2xy for the exponent, and then e to the x squared y. On bottom, we don't have to use a product rule here. Derivative of y is just x, and a derivative of xy with respect to y is just x, so that's where the x squared comes from. Derivative of cosine is negative sine. This term goes away in the denominator. Remember again, there's a plus 2x that's missing in here, so the derivative of the x squared on top. And then over here, we have, with respect to y, the derivative is x squared, so that's why the term out in front is just an x squared. And then this just pretties things up a little bit by factoring out the negative sign.